All right, so we've learned one way to find the greatest common divisor of 60 and 84 would be to use the prime factorization. But there turns out to be a pretty nifty and efficient algorithm called the Euclidean algorithm. Now here's the pseudocode. Essentially you start with x and y being the numbers a and b, and you look at the remainder of x mod y, and then you let x be the y that which is the number you were looking for, and then you let y be r. Now this is a little bit hard to follow, but essentially what we're doing is we're using the division algorithm, and you'll see that with some little manipulations we can actually simulate this pseudocode over here without actually tracing the code line by line. So basically here's how you're going to set up the Euclidean algorithm to find the GCD. You start off with the bigger number and you use the division algorithm to figure out the quotient and remainder when you divide by the smaller number. So 84 happens to be 1 times 60 plus 24. Okay? Now what you're going to do is you're going to take these two pieces over here and start as a new division algorithm. So the 60 is going to come over here, right? And then you're going to ask yourself, how many times do you multiply 24 to get to 60 and look for the quotient and remainder when you divide 24 by 60? Right, so r becomes the new divisor and y becomes the new dividend, right? The old divisor becomes the new dividend, the remainder becomes the new divisor, and you basically keep repeating the system, this process, until you get a y equal to 0. Once you get y equals 0, x, right, which is the number over here, is going to be your answer. Okay? So let's fill in the blanks. 2 times 24 is 48. 48 plus 12 is 60. Again, we repeat the process. 24 equals something times 12 plus something. Well, 24 is 2 times 12 plus 0. Once you see this 0 right here, right, you can stop. And the GCD is always going to be this number right here, right, which in this case will be 12. Okay? So we found the GCD of 60 and 84 in the previous video by doing the prime factorization of 60, doing the prime factorization of 84, and then looking for the common prime factors that went into both of these. Okay? It makes sense, it's direct, but it's a little bit tedious. This is a little bit more abstract. It's not exactly clear just by tracing through it what you're actually doing and why it works, but it can be proven to give it the correct answer. There's more details about that in the book. But this is a nice, efficient way that just involves simple modular arithmetic in order to get the answer. So let's try it on a bigger example and see with the second problem if we can get the hang of this. So we start off with the 480. We figure out how many times we'd have to multiply 264, find the quotient and remainder here. Right, well, it turns out that 264 goes in one time with the remainder of 216. And then again, we bring the 264 down. The 216 becomes our new divisor, and we find a remainder now in quotient. Well, 216 also goes into 264 one time with a remainder of 48. Shift over the 216 divided by 48, quotient and remainder. Turns out that 4 times 48 is 192. That leaves 24 behind as the remainder. 48 equals quotient and remainder when divided by 24. We get 2 times 24 and we get a 0, right? The 0 is the key to tell us we can stop doing this. The 24 is the answer. And within a few steps here of just simple integer division, we can use the GCD, the division algorithm, to find the GCD. Right? If you can remember how to do this process, I think it's quicker, but it does take some practice, and it's sort of easy to forget. Luckily, these things sort of come over in the right order. Once you've done it a few times, this can make your life a lot easier than the prime factorization. In general, unless you're specifically asked to use the Euclidean algorithm, either method works. I happen to prefer this one because it involves less calculations, but it's really a personal preference. Okay. Now what if we asked you for the LCM and you were using the Euclidean algorithm. Right? The way we found the LCM before was to use the prime factorization. So the advantage of doing the prime factorization is that you can get both the GCD and LCM from the same thing. Right? And it seems like we're losing some work here if we find the GCD this way because we're not any closer to finding the LCM. However, it turns out there's a nice property here that if you multiply the GCD and the LCM together, you're going to get the product. And you can do this by exploration a few times. If you look at the minimum and the maximum overlaps, you put those all together, you're going to end up with the number or the product itself. So let's say we wanted to figure out the LCM knowing the GCD of 60 and 84 is 12, right? If we've done the prime factorization, the LCM would be easy. But if we use the Euclidean algorithm to get the GCD, then we wouldn't want to go through that whole process of prime factorization. So what we can do is we can say 60 times 84, right, and figure out that product. That product is 5,040. And we know that 5,040 equals the 12 that we know is the GCD times the LCM. So if we divide by 12 on both sides, we'll get 420 equals the LCM. Right? So if you decide to go the prime factorization route, once you've done all that hard work for the prime factorization, you can get both the GCD and LCM quickly. If you decided you're going to use the Euclidean algorithm, which I think is easier to model this way than to try to trace through all the code, because this gets a little convoluted here. But you can also get the LCM by dividing the product of the original two numbers by the GCD, and that should give you the LCM. Okay. It's up to you to decide how much time and energy you want to spend on the Euclidean algorithm. You might decide to just go with the prime factorization route, but certainly from an algorithm perspective, prime factorization as computer code takes a lot of work to go through all the possible factors and determine which prime numbers are actually factors of a number. It's very tedious, it's very inefficient for a computer. This is super efficient and pretty clever. So give it some practice, you might find this easier.